Another case of diffraction is if we use X-rays and diffract those, just like we did diffraction or interference with visible light with the single and double slit diffraction. So in this lecture, I'm going to go over section 36-7, which is X-ray diffraction. So X-rays are part of the electromagnetic spectrum. They're at much higher energy than visible light or radio waves or microwaves. But just like those other light waves, then X-rays should diffract when they go through a small opening. So if you remember from the discussion about the single slit diffraction, that we found that we get a diffraction when the opening is much bigger than the actual wavelength of the light. So the wavelength of light has to be smaller than the opening, or else you're not going to get the interference pattern that you want. So that kind of sets the scale. That means that if we want to diffract with X-rays, we have to do it with an opening or a scale that's that's close to but bigger than the wavelength of an X-ray. So the wavelength, so X-ray wavelengths are on the order of 1 angstrom. So the unit is A with a little circle on top, which actually works out to be about 10 to the minus 10 meters, which actually also is on the atomic scale. So for X-ray diffraction, these X-rays are not going to be diffracting through some physical barrier on the human scale, where we just take a piece of paper and make a small hole in it, or we cut a small slit in some piece of plastic or cardboard. Instead, the openings are going to be between the atoms. Actually, you can also get diffraction when you go around an object. So if we had an object like a cylinder, and then we had waves propagating up toward that cylinder, then what you're going to get is diffraction around the edges of that cylinder. So the waves are then going to hit the cylinder and then kind of bend around the corners of but around the sides of that object. So you can get diffraction either with the waves going through an object or diffraction just off the corner of an object. And that's what's going to happen with X-rays and atoms. So what we're going to have is atoms. So we have these atoms, which are spaced periodically. So it's a nice periodic structure. And then as the X-rays come in, they're going to diffract around these objects. So you're going to get some bending of the X-ray light around the object. The other interesting thing about this atomic structure is that we have multiple layers as well. So the diffraction that we're going to be working on involves both a transmission and a reflection. So if we were to draw out our crystalline structure, we take some crystal, which is just periodic atoms in these planes. And then each of these planes of atoms are separated by a distance d. So the interplanar distance of the crystal. So then what happens is the plane waves come of the X-rays. So here's our X-rays right here. they impinge upon this crystalline structure, and then they're going to diffract around the atoms, but some of the light may go to the second level, and some of the light may interact with the first plane. And so what we would get is something more like this, where I've got the X-rays coming in, and then they bounce off. And they're going to bounce off at some angle theta. So basically the law of reflection. The angle of incidence theta is going to be equal to the angle of reflection theta. And then we'll have another wave of light come in this way, and it hits this atom and reflects back. What we're going to have, I could have another one, change of colors. Light comes in, hits here, reflects back. All of these are at this angle theta, because everything is periodic. And what we're going to get is the diffraction, the interference. So we're going to get some interference now between these X-rays, these waves of X-rays that are coming in. So let's analyze just two of the planes. So these planes of atoms are separated by this interatomic distance d. And then let me change the color again. So here's my first wave coming in, reflecting at an angle theta. And here's my second wave coming in, also reflecting at the angle theta. And so now what I can do is, if I draw this line which is perpendicular to the planes, so I have a perpendicular line between plane 1 and plane 2. And now if I look at this, I could draw another. Now I draw a line that's perpendicular to the blue lines, so that's a 90-degree angle right there. So if that's a right triangle, then that means that this angle here is 90 degrees minus theta, which makes this angle here theta, as well as that angle right there theta. Now, so if I look at this triangle right here, what I have is the distance d, the interatomic, the distance between the planes of atoms, and I have my angle theta right there, which means this length here is d sine theta. So that's the length that the wave is traveling. Now if I look at this, if I go back and look at this, I have these two parallel lines which have the same length to them. And these two parallel lines also have the same length to them. So the extra distance that the blue line is traveling is this distance here and this distance right here. And so in the end, if I want constructive interference, then I basically have to have a distance of twice of 2d sine theta. So if I look at, let me draw this again. If I just draw 1/2 of it, this is the distance d. This is the distance d sine theta. And this was the red line, and this was the blue line. If I go back up here. So here's the red line, right here. Here's the blue line right here. And so I've just taken this and I've drawn it out. So this is the extra distance, that d sine theta is the extra distance that the X-ray travels, the second line travels. And it does that twice. And so 2 times this extra distance that the one wave of light traveled is equal to m lambda, a multiple of the wavelength, where m is 1, 2, 3. And if this is the case, I get constructive interference. And this actually has a special name called Bragg's law, because it was actually experimentally determined by Bragg and his son. So father and son Braggs did experiments of scattering X-rays off of crystals, and they actually won the Nobel Prize because the first crystal that they really determined, crystalline structure, was that of diamond. And so they figured out the interatomic spacing for the carbon atoms in diamond, and for that they won the Nobel Prize. So basically with this formula right here, we can now calculate we can experimentally determine the distance between atoms, d, or the difference between the planes of the atoms, d, by taking an X-ray of known wavelength and scattering off of a crystal and measuring that distance between them, d. To make the wavelengths, that one, electrons circling around it and the energy levels, then if you were to knock out one electron, so if we had an electron in the ground state, and we sent in some light, knocked it out, so that electron leaves here, an electron in the second ground state is going to drop down to the first, and in so doing, it's going to emit an X-ray. And so that's how we produce X-rays for the experiment. So the last thing we consider is what we've measured now is the spacing between the planes of the crystal, like this. So we've measured d, and what would be good to know is now what is the actual atomic spacing. So we know the distance between the planes, but what about this spacing, which I've kind of drawn symmetrically? But what about this distance right here, the distance between the atoms? So it turns out you can, use the scattering to figure out the geometry of this case. So let's say we have a crystal of 2 atoms. So I've got the solid atom and the open atom circles, like this, something like this. And then what we've measured is the spacing of these planes, let's say. So the book has a picture of this, where if we just focus on this region right here, then what you get is a spacing of half a distance a, and then a whole distance a between the black atoms, and then a distance of 5d, which we measured between there. And so if you do a little work with Pythagorean theorem, you would get 5d squared is equal to a0 squared plus a0 over 2 squared. And when you work out all the mathematics of Pythagorean theorem, you would get a d of a0 divided by the square root of 20. So then a0 is the square root of 20 times d.